This S4, it's actually 2020 S4Q3. I don't know if the answers are out yet, but I'm pretty sure the exam doesn't count. But don't go telling people about it anyway. So I guess probably the last question of the last exam. Um, so it was a bit weird. It was some of it was a bit frustrating. So like usually like you have like the hard part and the easy part, right? And I felt like the hard part was a part that's getting to be more or less standard for seniors and stuff.
Yeah.
And we'll learn it today. Okay, it's called reverse reconstruction, and the easy part, which is kind of like the part where you had to just do some formulas. Okay, it turned out to be actually really hard to execute.
Right.
Okay, so it was kind of a bit weird because usually when you see what's going on and understand the problem, it's fine. But this, it's like it's almost like it gets harder with the more you know, but the less you understand.
Right.
Because you have too many choices. I'll explain it. So, lengths of triangles. Here's the length. Okay. Alright, so what is the problem? That's a good question. So I think a lot of people have difficulty drawing the diagram for this problem. And you can see I have like 14 pages of rough working just trying to draw the diagram properly. Okay, well that's in the wrong section. So I'm not the person to go to for good diagrams. I kind of draw pretty bad diagrams, and that's why I have to draw so many. So if you get a compass and a ruler and have good habits from the beginning, you'll save a lot of work. Okay. Um, yeah, I'm the one who I can't really change my habits now, and also with the kids, I'm forced to kind of just sometimes even think about it in my head because I have to put them to sleep and stuff. So I can appreciate the difference a good diagram makes.
Yes.
Okay, so one way to draw the diagram, I think, is to draw a big circle, yeah? That's one way to do it. Draw the diameter, yeah? Okay.
And draw another circle.
Draw another circle that touches, yeah? For example, like that.
Wait, isn't it meant to touch the...
Oh yeah, it's a right, for juniors it was a right angle, but for the seniors it was not. We could go through both at once, yeah? Okay, so...
Let's do it.
Okay, so this is for a general triangle. Okay. So it's a little bit weird. You have like a side of the triangle. So this is C, yeah? This is A. This is that touches there, yeah?
Yes.
B. We're not going to use this angle.
Yes.
Okay. There's a point of contact here. Okay. I guess we don't use this side of the diagram. So can I erase this? Another way you might want to draw the diagram is, and obviously you have to be kind of aware of the cases where they're obtuse and acute and stuff. Obviously, this doesn't matter between B and C, but I think it might matter for A because of the definition. Okay, so you have. So you could also draw the triangle first, right? And then this is the altitude. So this is like a reverse reconstruction, right? You're drawing the conclusion. Okay. Oh, I haven't even I haven't even drawn in the midpoints yet. Okay. So this one, and the thing is, if you have a good diagram with a compass and everything, um, like you're gonna see, that the circles touch. You know, like that's gonna be helpful. So what is this? You take a midpoint here, right? So angle bisectors to the in center. Okay. And you take the midpoint, yeah? Make it 90 degrees.
Yes.
And that's okay, yeah?
Ah.
So that's a bit more mysterious, yeah? You don't know if the circle touches or not. So this is C. This is B. Okay. I'm just continuing with this diagram. So this is where you start with the triangle, right? There's a circle here. And then you draw another circle. Yeah?
Mm-hmm.
Yeah. Yeah. Okay, so this is the midpoint. Yeah. Fix the dodgy line.
Dodgy line.
You mean this one? I'm not at the point where the dodgy line uniquely specifies the thing that needs to be fixed. Okay, I don't know if that fixed anything. Anyway, so this is like a reverse reconstruction, right? You got a circle. You go to the end of the diameter, okay? And then, so there's an in center. There's a center for this circle. Yeah. The center's called I.
But the one, if you fix it, then it will meet at N. He means the line AI on the second. But like, if you make it too straight, it will like go into M.
Yeah, like one of the hard things about that line is it keeps going into M, yeah? Alright. So now you can go from K, right? K goes somewhere. Okay, so can you see that because it's perpendicular to the A, right? AI, it has to go through the point on the circle, yeah? That's helpful. Let's see reverse reconstruction. Yeah? Now you can call this point Q. And this is meant to be M, right? Yeah, reverse reconstruction. I don't really know what the definition of reverse reconstruction is per se because I used to do this thing all the time and the people kept telling me it's called reverse reconstruction. But basically, it's like you assume what you need to prove. You're basically trying to do the converse of the thing that's asked for. Okay, so instead of going for the triangle and the in center first, and then seeing if the circle touches, you first assume that the circle touches and see what has to happen. Okay, so this was a general problem-solving technique where you kind of just assume the conclusion, right? see what implications the conclusion has, and then you try to prove those things instead. Okay, and then maybe you can sort of strengthen your way up to the actual conclusion then. Yeah. So for geometry, it's particularly useful because a lot of theorems actually imply their converse, right? Because there's not so many places the points can go once you put them there. Okay, so basically the two parts of this problem was sort of realizing that. So for me, anyway, this is how I did it. If you have a tangent circle here, right, you kind of need to realize that first of all, it's unique. Okay, so what I mean by that, it's like if you fix A, right, and you vary K, right.
Mm-hmm.
Okay. Basically, if it's already touching at that point, yeah, you can see if you move M a little bit, it's gonna go up a little bit, right? And then it's no longer gonna be touching, yeah.
Mm-hmm.
So this point is unique for that point of touching, yeah. And then there's only one point touching, okay.
Yeah.
Okay. So if you notice, if you make this 90 degrees, that's the altitude, right? It's actually parallel to the radius, yeah? So it's parallel to the radius, or diameter even there, right? Okay. So if you drew a line, right, from A through that point, yeah, to the inside, it's meant to actually hit this point. You know it actually hits that point, okay? Um, okay, well, we'll see, okay? Okay. So I guess depending on how you do it, if you already have the circles drawn, you might just want to draw the line that goes to the point of contact, yeah? And then you want to see that it goes through that point, yeah? So what you can do is you can now go through. So basically, you can join it to the point of contact. And then you join it down there, yeah? Okay. So if we just joined it to the point of contact, yeah, then we know that we know it's 90 degrees, right?
Yeah.
Okay. And trust me, this was not something like you can do with a bad diagram. I had to improve my diagram before I could do this. But basically the point is, you know it's 90 degrees, right? Because of the diameter. So the chord that it makes on the small circle has to also be 90 degrees,
Oh.
right?
Yeah.
Okay, so that means the chord has to be a diameter, right? So you just have to know that the diameter that makes that 90 degrees is parallel to this diameter, and then you know it works, right? So, I mean, this is also true for a 90-degree triangle. I think there might be some simplifications with 90 degrees, but let's just look at this because there's some things we can learn here, okay? Yeah, so we're kind of gonna. So the plan for the proof is to see what happens backwards, right? And then show that that's the only way it can happen, right?
Mm-hmm.
And that every possible in circle is gotten by this way, right? And then we show that the argument's basically reversible. Okay. Anyway, so basically the point I'm trying to make is it has to now pass through these. There's only one vertical diameter, yeah. So that has to be that one, right? So that's kind of nice. So basically that tells you for one that the point of contact is unique, right? because it can be gotten by drawing A to the ends of this diameter, which you already have, right? And joining them, and I guess you have to show that they intersect, right? That's the problem, yeah? So that's kind of what makes it hard. You just have to show that they intersect, okay? But the point is, like, if you do have a situation where it's contacting, if it can contact, then it's unique, right? Okay? So that's one thing that you need to be convinced of. Another thing you need to be convinced of is you can sort of get any circle configuration this way, you know? So if you kind of draw a vertical line, you can imagine sort of drawing any triangle you want, you know? So sort of having any kind of place for the horizontal line, and then any two angles made at A, right? It could even go this way, yeah? For example.
Yeah.
And then the in circle can be made to touch, okay? So, and it basically is, so if you don't have the big circle, you basically just have to form the big circle by doing this intersection, right? That makes sense?
Yeah.
So if you draw the line through the diameter here, there, and then through this point, wherever it goes here will end up having to be the diameter of the circle that touches.
Yeah.
Okay?
Mm-hmm.
So every triangle in center, in circle, can be touched in this way.
Yes.
Okay? Okay, and when it does, it's a unique point K and a unique radius for this circle. Okay? That makes sense? So this part of it actually would be the hard part for juniors and intermediates. Okay? But by the time you're getting to senior, this is becoming more or less standard. I guess by that time you kind of solved enough problems to kind of be like, oh, that thing's coming up a lot. And I don't know the reason, so like I haven't solved enough geometry problems to really nut down the reason for it. Okay? So there's two possibilities. There's the fact that geometry is just intrinsically two directional with logic. Everything works backwards as easy as it goes forwards. Okay? Or problems are just easy to make that way. It's easy to make a problem in one direction and then give it to the people backwards. Yeah? So that's a cynical view, but it's also possible. So that's why we're trying to get into the habit of natural problem solving, right? Because you don't want to get in the habit of, oh, I need to sort of do a million practice problems, then I can solve the problem because I know the problems amongst them, right? You want to have like a natural thing that when you actually get out in real life, you'll be like, oh, I have this. I can wing all these situations without having necessarily the exact experience, right? Okay. Okay. So once you draw the diameter, right, you know that point K, yeah? So then AI is also a fixed length, yeah? A fixed line. So then there's exactly one line perpendicular to that line that passes through K, right? And notice that when they intersect, it has to be at a right angles, means that it's on the circle as well, okay? So you have that this extends to a point on the BC, right? Okay. So the only question then, see, this is kind of the hard and interesting part of the problem, right? Because you're like, oh, why is it even doing this? But so now we know that there is a point on BC, right? And there's only one for which this construction can work, yeah? Mm-hmm. And if you think about it another way, if you move the point M, obviously it's going to make the circle smaller, right? Yeah. And if the circle gets any smaller, it's no longer going to touch. Yeah? Mm-hmm. If it moves the other way, it's going to get bigger, and then it's not going to touch again, right? It's a very delicate equilibrium that exists. So then all you would have to show is that M would have to be the midpoint. Okay? Yeah. Okay? And if you could show that M was the midpoint, then you can go in the converse direction and say, well, if M was the midpoint, you can get this, and it's all back, and then it is what you want. Okay? Does that make sense? Yeah. Okay. So that's like, sort of like the first step, okay? Now the second step comes from actually finding that point, yeah? To actually find that point as the midpoint. Alright, so actually, the seniors will appreciate maybe an explanation for this, okay? So like, why is it that it's touching the two circles, yeah? So unfortunately, this explanation doesn't come into the proof, which is kind of weird. But or maybe you can make it come into the proof, but it's actually a very simple explanation, okay? So if you have this thing called inversion, right? And you invert about k, okay? So what inversion does is it sends lines that don't go through k to circles that go through k, okay? And the point is, if you invert it such that C goes to A, right? And then Q goes to M, yeah? Then the line CM has to go to the circle KQA, right? Right? And so I won't go on too long about this because the juniors probably don't understand this, but and if you do that, right, it actually fixes this circle. This circle here is invariant under this inversion, okay? Because this point is on this line, right?
Yeah.
So it has to go to that point of contact, right, on the circle, okay? So this line is tangent to the circle, yeah? So it'll be tangent to the image as well, yeah? So the image is fixed, so it's still going to be the inner circle. The image of the line is the circle here.
Yes, that one.
So then this tangent point becomes that tangent point under inversion, okay? So that was like, I don't know, a whole bunch of rough working, maybe here. Yeah. Okay. So I guess understanding the problem. So once you're at this stage, I think you should have at least like confidence, or even at least false confidence that you can solve the problem now. Okay. Because look what you have to do now. All you have to do is find this point, intersect it on this line, and find where that line is. Yeah? Okay. Well, I guess it's easier said than done. And this is what got me like sort of the most frustrated. I was always on the balance between, oh, should I do this or should we do it together?
Yes.
And I guess I decided that we were going to do it together, but as I decided that, I ended up doing it anyway.
Oh.
Okay, so how do we do this? Okay, maybe I can show you one more step before we get to the thing. Okay. One more step. Okay, so this part, next part, you can get this point using coordinate geometry, right? You don't have to use coordinate geometry, okay? But I mean, it's essentially the same. It's just one way is kind of more obvious than another way, okay? So I don't know. To make it more elegant, you can try and do it without coordinate geometry. So for example, what is this point here called? O. What's that point? O? Maybe D. D is more standard, I guess. So for example, you could make this the origin, yeah? Let me use another color for this. Yeah, let's make all this artificial stuff we're drawing in red. Yeah, so what if we make D the origin, yeah? So A would be the height of the triangle, yeah? So we're gonna call it 0h, yeah? So here's a funny thing, can you just let that be 1? I was always asking this, it's like, oh, you probably could, but then you have to scale the other stuff by what the length is. So I kind of just like, I left it as X. Maybe I made this positive in this direction, yeah? So this is X, comma 0. And this will be X, comma R for the in radius, yeah? And then this can be 2R, yeah? Minus H. Yeah?
Yeah.
This will be negative, so H minus 2R. Where R is the big radius, yeah?
Wait, why? Oh, big up, okay.
Yeah.
Yeah, then you can find M because like you take the line AI, and then you find the equation for that line.
Yeah.
And then you find the perpendicular going through.
Yeah. So you don't even need the equation of that line, right? You just need the slope.
Oh yeah.
So if you want to do this with coordinate geometry, oh, you know the last one we did with coordinate geometry, I would say it was like my first ever chord bash. Because that's like the only one I really, it was on Tuesday, did you see it? Anyway. Yeah, you weren't here, but you could have watched the video. Another time, maybe.
Yes.
Okay, so so you know, for example, the line passing through this, right? It's like y equals mx. I'll use capital X because little x is taken. Mx plus b, right? And b is just h minus 2r. And the gradient is this gradient here, right? So it's so this is r minus h on x, right? Is the gradient from these 2 points. And then you want the negative reciprocal for the perpendicular line, right? So it's x on h minus r. Yeah. And then to find, so that's the equation of the line KQ, right?
Yeah.
So this is equation of KQ. So obviously I'm not showing you my actual solution, I'm just showing you the rough working, but this is very important. So to find out m, we just need to set y equals 0, right? For m. So m equals, and it's going to be something 0, right?
Mm-hmm.
So it's 2r minus h.
That's like basically what I got.
Yeah. You're assuming it's wrong just because you got it. That's rather negative.
Simplify to like the big one.
Yeah, I mean it shouldn't, right?
Oh, it shouldn't. What?
Because so look at this. So this should never simplify to the midpoint, okay?
Oh.
Because it has made no assumption that it actually is tangent, okay?
Oh.
Make sense? This is any diameter at all. This is perpendicular there, right?
Oh.
So this is all the possible m's along BC, yeah?
Yeah.
Only when you fix r do you fix m, okay? But what this does tell you is that there's a one-to-one relationship between r and m, yeah?
Yeah.
So for every r, there's one m.
Mm-hmm.
For every m, there's one r,
Yeah.
yeah? Right? Because this doesn't assume anything about the circles, okay? But once you fix r, there's only one m, okay? So how do you fix r? Well, you need to use something here, right? So there are lots of different things you could use, but I found the easiest thing to use, okay? The easiest thing that I found to use was that, okay, and you might have to check this, okay? So when you have a tangent contact, right? The point is the point of contact goes through the two centers, okay? So the easiest thing that I had to use was that the distance between the two centers, okay? Maybe call it O, yeah? Oh, this doesn't look collinear at all. Okay, let's call O the center. It's the midpoint of AK, right? Yeah, so the fact that the point of contact, maybe we call it P, and the O is getting confused with origin, but the point is P, I, O is collinear, right? So after making that observation, the easiest relation that takes into account that they're actually tangent to each other is the radiuses add up to each other, right? So basically, I'm trying to say that this point O, where should I draw it? D is the origin, okay? It's like another point O, which is the center of the circle, yeah? It has coordinates h minus r, yeah? Yeah? Okay. It passes through there, right?
Mm-hmm.
So the distance between O and I, yeah? Yeah? Should equal big R minus little r, yeah?
Oh yeah.
Okay. So this is nice because it's not that complicated, right? And I think a lot of the difficulty in this problem is that you actually have a lot of different choices. A lot of the time you don't know what to do. This is that you have too many things to do. And the more senior you are, the more options you have. So you become sort of like I don't know, bombarded by choices. And you, as the saying goes, the mathematician is afraid of choices because that's when you can make a mistake. If there's only one way to go, you can't make a mistake, right? Okay, so you make a choice like this, it's r minus I, and then you can find the distance between these points, right? By just coordinates.
Yeah.
Okay, so you can make use of that condition. Yeah, I remember when I was in the US, there was this market of choice. I've told this story a few times now, but it was like, why would you ever want to go to the market of choice? That'd be the scariest place ever. They would just always make you choose unnecessarily when there might be like a good standard option.
Yeah.
But then I realized that it could have meant that it was the market of choice, as in you didn't have to choose which market you went to. It was the best one, so you could just go there. I don't know what they were intending, but they had a lot of choices inside. That's for sure. Okay, it was a little bit expensive too. Anyway, so OR equals R minus R. So what does that give you? OR equals R minus R. So the OR has got a simple distance formula, right? So it's x squared. So the distance squared is that squared, yeah? Yeah? Okay. I mean, when I was doing this, I made some calculation errors as well, but I fixed them after an inappropriate amount of time. Okay. So I think this gets you kind of complicated because there's lots of variables and sometimes it gets confusing what to do because you forget your goal, okay? So, and I guess part of it is actually realizing your goal, okay? So here it's tempting to solve for like x
Yeah.
because I guess x is always what you're solving for in the exercises. But what you really want to do is solve for r, right?
Oh.
Yeah? And I'll tell you the goal as it becomes more clear anyway. So once you solve for r, so what do you get? Now be careful, this doesn't cancel, right?
That's it. No.
Some of it cancels. So the squared terms cancel, right?
Yeah.
So you got x squared minus 2hr minus 2hr, right? Minus 2rr, yeah? And then the other two squared terms,
Wait, how about the h squared?
yeah, can't get anything past you, huh? Alright, so we get the other two, oh, it completely cancels, yeah? The right, actually no, this is a plus,
Yeah.
okay? So this is r squared cancel with that r squared cancels here, and then you get minus 2 r, right?
Yeah.
Alright, let's see. Yeah, my video is still not broken, hopefully. Okay, so sure you can solve for x, but it doesn't help you that much, right? It doesn't mean you won't do it.
Yes.
Depending on your state of mind, I think there'll be sometimes you'll solve for x, sometimes you'll solve for h. There's a choice, right?
Yeah.
Okay, so if you do that, it turns out to be a little bit messier. I think a nicer way to do this, and for some reason it's always been the case that when you do a different two squares, it gets a nicer answer and quicker. Okay, so that if you do x squared equals the difference of two squares, you get x squared equals, and it becomes, yeah, so h minus 2r, right?
Yeah.
H minus 2 big R, yeah?
Ah.
Or is it 2 big R minus H? 2 big R minus H, yeah? Yeah, 2 big R minus H. So when you subtract it, it's 2 big R minus H, yeah? Yeah, so I'm trying to highlight it's not all straightforward because sometimes you see the nicest, cleanest solution, but you don't see all the choices that you could have made on the way, yeah? Okay, so that's right, yeah?
Yeah.
So it's
That.
minus H in one of them and plus H in the other one, right?
Yeah.
And then they have opposite signs.
Yeah. Yeah.
Okay. Well, anyway, we'll be off by a sign at most. See, that's the kind of thing.
Yeah.
But it could, so okay, then you have like 2r. See, now it's easier, right? You can actually just straight away do 2r minus h, yeah?
Oh. Ah.
And so then m equals, so this is all in red. Is red even visible? Okay. You have m. M is x, h minus r, h minus 2r. Yeah. And so this kind of satisfies the goal of what we're looking for, okay? Because it expresses m, right? entirely in terms of the triangle. Does that make sense?
Yeah.
So this is a property of the triangle now, right?
Mm-hmm.
So even if it wasn't the midpoint, it would consistently be one point on the triangle somewhere.
Yeah.
Because the height, the radius, in radius, and the point of contact, they're all intrinsic to the triangle, right?
Mm-hmm.
That makes sense?
Yeah.
So, this could have been the question, right? Yeah, it just so happens this simplifies to the midpoint. Okay? Let me put this here. So m equals.
Wait.
It must, right?
Yeah.
So we have to see that it does, but it must.
Yeah.
But that's kind of the thing, is you're forcing the problem to reach a conclusion, yeah?
Mm-hmm.
So the problem is we don't understand why it's the midpoint,
Yeah.
So at first I thought it might have something to do with the fact that Q is the midpoint of P. It's like the mid arc of P and the extension of C, yeah?
Yeah.
But that's not true because you could have made this as big as you want, right?
Mm.
And it'll always be the case, but none of those give you the diameter, right? So that's a red herring right there. Okay? If you wanted a more elegant way, well, not elegant, but just if you wanted to look coordinate free, but it's still not coordinate free, it's just another way of doing it. You could have, for example, let's see, coordinate free ways of doing this. You could have equated, so I mean, realizing that mt on tk is t, or t is d. So md on mk Oh, okay. So you could have also taken, basically realizing this triangle and like another triangle are similar, right?
Yeah.
Is another way to do it.
Yeah.
Okay. So, for example, which is equivalent to saying because they're right triangles, the tan theta or something is the same, right? So here tan theta is equal to, um, you know, 2r minus h on md, right?
Yeah.
And it's also equal to, like, for example, this angle up the top, right?
Oh yeah.
Yeah. So you can draw like a triangle here, for example, which you get h minus. So it's like, what's that length? H minus little r, right?
Mm-hmm.
Okay, so then tan theta is also equal to uh, x on h minus little r, right?
Yeah.
So you get the same thing, yeah? md equals 2r minus h on x, yeah?
Yeah.
And then,
Wait. Oh.
okay,
Mm-hmm.
and you can use a similar kind of condition to get rid of the big R, yeah?
Yeah.
Okay, we don't really want to go through this. I've just lost interest in going through that part.
Yeah.
Did you want to go through it?
Is that a faster way of doing
A faster way of doing it? Oh, okay. You mean like finding the big R?
it? Yeah. Or just like,
of getting this step.
Or like just another like to get that step in between.
I mean, this is 2 steps, right?
Yeah. Like
I don't know if you can get any faster. I mean, the time it takes to think of something is not trivial.
yeah.
You mean a faster way given. Mm, you could maybe do the slopes of these and multiply them to -1 or something.
Yeah.
Yeah. See, the slopes of these, um, you have an expression in x, r, h, x, and r, right?
Mm-hmm.
So if you multiply the slopes together,
Yeah.
you know, which in a sense is still using this angle, right? You know. But I mean, the thing is, like when you're doing stuff with length, it's so completely transported into coordinate geometry. Having or not having coordinates, it's kind of um, it's just more or less of aesthetic.
Yeah.
Okay. All right. Okay, so this is reverse reconstruction done. Okay. So okay, so this is the point. This is the different distance between the point of contact and there. So there's a triangle that's involved. Okay. Let's draw this triangle. Mm-hmm. Do you have a name for this point? It's already quite a few points. So there's like x is the point that. So this is where it can get a bit complicated. You have to worry about if things are on the left or the right of stuff. Okay. So you have like the angle bisector hitting at x. You have like the midpoint. I guess it's M, or sometimes they call it A prime. Yeah. And you have actually C, which is the thing. You have B. Who would have thought the actual vertex of the triangle would be a complication? And then you have the altitude. Yeah, so actually a lot of these lengths are known, okay? So this is where I maybe wanted to give you a bit of a review, because you missed this when we did it.
Oh.
So this is chapter 1 in Geometry Revisited, okay? So I don't know if you remember this, but so the claim that I'm trying to make is, so, general notation for this kind of stuff is like this is called C, right? The side opposite to big C. This is called B, yeah? This is probably called HA, or in our case it's H, right? Or H sub A. Um, Now, so it's actually known that this length here. So there was an exercise that actually tells you what this length is, if you don't know. So this was, so in this, if C is bigger than B, it's C squared minus B squared on 2A, okay? Um, the in circle stuff tells us X, we know the length of XC, okay? Is actually S minus, um, the vertex that it's at, C, and yeah, and obviously like that'll give you you can figure out some of the other distances too there, right?
Yeah.
Um,
You can do just like CD and BD with Python.
yeah. Oh, with just these two relations, you also get like mx.
Yeah, like
Mm.
after that CD.
Yeah, and you know that this is, you obviously know this is half a, right?
Oh
Yeah.
yeah.
So this whole thing is called a, yeah.
Okay.
Okay, and all of these can be found in Geometry Revisit Chapter 1, okay? And maybe I can quickly go through some of it for you. So if you're doing AIMO, for example, like a lot of this is not necessary. Like, okay, let me explain what's necessary. Like, what's part of what? Okay. So if you have like a circle, it's in a circle, right? So that's gonna be like our x, yeah. This is A, B, C, yeah. So it contacts the points. So you know they contact at 90 degrees, right?
Mm-hmm.
It's the shortest distance from a point to a line, yeah? All the other ones have at least the radius.
Yeah.
Okay, so the way it works is these are the same, yeah? And these are the same, and these are the same, yeah?
Yeah.
Oh, by the way, I should tell you what S means. S is
Semi-perimeter.
equal to the semi-perimeter, so half the perimeter, yeah? Okay, so can you see that basically, like, if you call this X, and this calls Y, and this is called Z, right? Okay, so in AIMO, I feel like just from all the questions I've done, you don't actually need to know exactly what they're equal to. You just need to know that they're equal. And drawing those tangent things actually solve a lot of problems in AIMO. Okay? But when it gets harder, like more AMO, you might start needing these lengths. In this case, it helps a lot. Okay? This is the last question of the selection test. Anyway, so okay, the point is that they're all equal. So x plus y plus z, right, is equal to s, right? Because 2x plus 2y plus 2z is the perimeter. Okay? And so then if you look at like z, for example, right, z is just s minus x plus y, right? Yeah? Or x is equal to s minus x plus y, right?
Yeah.
Oh, z plus y, sorry.
Yeah.
Okay, but z plus y is like one of the sides, isn't it? It's a.
Oh.
Yeah? So that means x is actually equal to s minus a.
Oh.
Okay? So basically, the conclusion is it's s minus whatever the vertex is. So if it's big A, then it's s minus little a. Big C, it's s minus little c. And big B is s minus little b, right? So in this case, it's s minus little c here. Little a, or little c, yeah? This is a big C here. Okay? Jeez. Okay. Should we verify the other one, or can we assume it? Should I keep the diagram over here? I'll put the diagram over here. See, is it always in this order? It's hard to tell depending on the size of these things. Yeah. B, X, C. Okay. So then one strategy, given that this is what we have, right, is to express everything we have in terms of A, B's, and C's. Yeah?
Mm-hmm.
If we express everything you have in terms of A, B's, and C's, it's going to work, okay? And at this point, for some reason, I was like, sure, it probably should work, but I wasn't necessarily sure we had the right answer at this point. And it wasn't obvious how complicated the expressions are going to be.
Yeah.
Okay? I don't know if you wanted to explain this one. You happy with this one?
Right.
We could go over this one if you want. Is there any feedback from the chat? But given the form of the formula, you can kind of chase these right angles, right?
Yeah.
Do you want to try it? I never actually did it. I just assumed it, but so what's c squared minus b squared? Let's call this length like call this length w, okay?
Mm-hmm.
So c squared minus b squared, yeah,
Mm-hmm.
is equal to, so b squared is h squared plus w squared, right?
Yeah.
Now c squared minus h squared is equal to
A plus W.
a plus w squared, right?
Mm-hmm.
Okay, now difference of two squares. So we're learning from before, I guess. Is a outside of
A plus 2W.
a plus 2w, yeah?
Mm-hmm.
Okay. It's a little bit awkward. A minus. This formula, this doesn't. This is not true or what?
For
Huh?
divide by 2A. A plus 2W. Oh yeah, that's just correct.
Is it?
If you divide by 2A, you get A plus 2W over 2, right? Which is A over 2 plus W, which is correct.
Yeah.
Yeah. Because
That's a over 2 plus w, right?
Yeah.
Alright, excellent. So we divide by a. Yeah. So it's different to check something than it is to prove it. Okay.
Yeah.
Oh my gosh. Okay. Okay, so we can be confident in those things. Yeah, I have a bigger headache right now. Okay, so what are we doing? Okay, we're trying to evaluate this expression, right? Can people see purple? X h minus r on h minus 2r, right? Okay, so one idea that would work, okay, but may or may not work depending on how much time you have. So I tried, for example, to look for, divide this by h, right? And you get, so I tried to look for these ratios in the diagram, yeah? So one thing that kind of came up was, oh, by the way, before I finish, I don't know if this is needed or not, but there's one more thing I want to tell you about angle bisectors. So like if you have the triangle, right, and that's the angle bisector, then the ratio of these two sides, so this is C and this is B, yeah, is C is to B, yeah? You know that? That's called the angle bisector thing. So it may or may not come up, but that's this point here, yeah? So that's the sort of complete the toolbox. And this is a nice example. So this is a common thing that happens very early on. It's calculating the area of a triangle in two different ways. Okay? So because the bisector is always equidistant from the two sides, right? The area, so these are equal, yeah?
Yeah.
So the area is proportional to this, and it's proportional to the base and this.
Oh, yeah.
That makes sense?
Mm-hmm.
So, let's see. So the area is base times height. So it's B times H plus, it's B times H to C times H, right? And they have the same height on this side, yeah? What am I doing here? So this is like X to Y, yeah? Let's use different letters, Z to Y. So C times this height to B times this height, yeah? They're the same heights, is equal to Z times that height to Y times that height, yeah? Right, and it's another height as well, yeah? It's the same. So that means this should be C and this should be B, yeah? This should be B. Okay, so I should also put in that this is another point here, maybe Q prime. It's C is to B, yeah? Yeah?
Mm-hmm.
Oh my gosh. I don't know if I get through this whole thing. Okay. It's in black. Now we're ready, okay? X H minus R X H minus 2R, right? And maybe you could think of this as dividing by H as 1 minus R on H on 1 minus 2R on H, yeah? Okay, so I feel this might be the last ever one of these questions I do, unless there's lots of people who want to watch it, because yeah, there's only so many times you can do this. Okay, so R over H is this length over this length, right? So for example, you could calculate it as this over that because they're parallel, yeah?
Yeah.
Right? You could do that and you'll get everything in terms of A, B's, and C's because you have these lengths, right?
Yeah.
Okay. Oh, let's actually do it for the 90-degree case because that's what the actual question was asking, yeah? So let's do it. So I wasn't actually so this is not the order this happened, okay? But we have that in mind. It'll get you something, right? But it was only when I did the 90-degree calculation was I convinced that this was going to work, okay? So, you know, when it's 90 degrees, what's x, right? So what happens if it's 90 degrees?
Because you can make square.
X is just, oh yeah, is it?
I think. Wait, let me.
You already did that.
Well, that's.
It probably end up the same. You can check, okay? But anyway, so S minus C is sort of the most obvious one from this formula, yeah?
Oh.
The C is all the way here, right? So this distance is just S minus C, right? So X becomes S minus C. Yeah?
Yeah.
H minus R. So remember now H is just B, right?
Mm-hmm.
Yeah? This is just B minus R, yeah?
Yeah, it is equal to R.
Oh, okay, cool. And then H minus H minus 2R is B minus 2R, yeah? And then you need to get to R somehow, right? But then you notice that the area of the right angle triangle is just B times A, right? On 2. Yeah? So you notice that when you do a triangle with an in circle, right? The radius times the perimeter is what gives you the area, yeah? Because that's the radius. You add this base to that base to this base to this base, and you get the area of the three triangles, right?
Mm-hmm.
So RS is equal to the area, okay? And in this case, it's equal to H, which is B times A on 2, yeah? Okay. Okay, so this is equal to S minus C times B minus BA on 2S, yeah?
Yeah.
On B minus yeah, AB on S.
Yeah.
Yeah. Okay, so
Yeah, and then everything's in terms of A, B, and C. Because S is C.
yeah, so now it's all what you want, right? It's just a simplification now. So no, you can do some obvious stuff now, right? Clear denominators, cancel the b's, yeah? So S minus C becomes, and then you can times everything by S, so you can times everything by 2S even. So you get 2S minus A on 2S minus 2AB, A, yeah?
Yeah.
Okay.
2S is just A plus B plus C. So that bit is just B plus C.
Yes. So this is B plus C, right?
Yeah.
So this is not B plus. This is half A plus half B minus half C, right?
Yeah.
This is A B plus C, yeah.
Yeah. And that one is B plus C minus A.
B plus C minus A, yeah.
Yeah.
So notice the B plus C minus A should cancel. Okay, anyway, so let's see what happens. You have basically 2B plus C minus A at the bottom, yeah?
Yeah.
A plus B minus C. So I have A times B plus C, yeah? Plus B minus C times B plus C. You know? Actually, this is something I should really just let people do themselves. Oh. Yeah, so Pythagoras, yeah, it's a right angle triangle now. So this is minus A squared, right?
Yeah.
So this is A B plus C minus A squared, so you get a minus A in there, right? And they cancel. You get A on 2.
Oh. Wow.
And that's the midpoint, right?
Yes.
Okay. Okay, so when it's not 9 degrees, let's see what happens. So X. So I was saying you could do that ratio and it gets pretty complicated, yeah?
Mm-hmm.
Or you could use that idea we just got from the right angle triangles, yeah? The idea that RS is equal to H A on 2, yeah? That's true here even. Yeah?
Mm-hmm.
So it's equal to that. So R on H is equal to A on 2S, yeah? So it's equal to X 1 minus A on 2S on 1 minus A on S, yeah? Oh. Okay, so some of this is getting diagram dependent. You may have to make some comments, but I'm doing it for this diagram, okay? The diagram dependent means like if this is on the other side of it, or maybe you always know that it's on one side of it, yeah? Okay. Alright. What's X? So we have some formulas for X, yeah?
Yeah.
So maybe X can be regarded as um, the purple point minus do we know the distance there? We could do X minus so we're going to do X minus C, yeah? Get that part. Or we could do like X minus this part. You think I would get X? So for example, given the formulas we have, right?
Yeah.
Like to get X, you might want to go like the midpoint, yeah? Minus minus half the length plus the tangent part, yeah? There's one way to get it, yeah?
Yeah.
So you have like x is equal to, so in this case it's c squared minus b squared on 2a, right? Minus a on 2, yeah? To get back to c.
Yeah.
And then plus s minus c.
Yeah.
To get to x, yeah? That's one way of doing it. And that'll give you, so for example, this is c squared minus b squared on 2a, and the a on 2 cancels there to get a plus b on 2 minus c on 2, right?
Yeah.
There's a common factor of b minus c, yeah? C minus b on 2. So c minus b on 2. And then it's maybe 2a, we can take out the 2a as well. C plus b minus a, right? Yeah. So that's x. So notice what we're trying to show actually. We're trying to show the midpoint, right, is equal to, like we're trying to show that it's equal to c squared minus b squared on 2a, right?
Yeah.
So we got the 2a, we got the c minus b, yeah? So we just need to show that this part times the other part, right,
Yeah.
equals c plus b, right? So now we just need to show h minus r on h minus 2r, right? We need to show that this is equal to, so c plus b on c plus b minus a, right?
Yeah.
Yeah? Okay. Okay, so we have this, right? This is times by s. We can have 2s minus a on 2s minus 2a, yeah? So you can feel like it's going to get there, right?
Yeah.
Does it get there? Is it upside down? Oh, no. This is the 2s is already, s is half, yeah?
Oh, yeah.
So 2s minus a is b plus c, yeah?
Now it's b plus r.
Oh.
Oh.
B plus c minus a.
Whoa, we did it again.
Oh my gosh. Yeah, I mean, I didn't even write any of this stuff down because I knew once you knew the area thing, okay, and it worked for 9 degrees, it was going to work, okay? So, yeah. Any questions? A little bit hectic, huh? Yeah, so let me just summarize the proof basically. So we basically showed there's a one-to-one correspondence to this m and this k, right?
Yeah.
Okay, and then there's only one value that makes it do this. Okay, and then that has to be a half. And when it is a half, it works. Okay? Okay, and then this part, like it could actually be quite epic if you think about it, because if you did it another way, you can get a lot of squares and you have to factor and cancel. So, yeah, I mean, I'll try to upload a picture of the working, but what do you have here? So it's just like a lot of random scribbles, yeah?
Yeah.
So that was the 90-degree thing. And that was, yeah, see, I just finished that used S equals, and that's it. And then there was some inversion stuff before that. Okay, so I considered inverting about point K, inverting about point A. Okay. And even though they didn't come up, they really helped you understand it, okay? Because there's no way that this can be false now, right? It's an exact correspondence between the two tangent points. So the tangent when the line is tangent here goes to the tangents between the circles there, okay? And then this is just, I don't know. I think it's important you understand how the formulas come about. So the idea of trig, that these side lengths should be determined in terms of the side lengths, because the side lengths determine the triangle up to congruency, okay? And I think you should know some of them. And as I was saying, you don't need like this kind of detail for AIMO, right? But obviously it could help you if you knew how to use it. Yeah, the more exact lengths are more useful for AMO. Okay, I'm gonna end that thing with that. Yeah, and I mean this took ages. This is not like 5 second stuff. But you can see that the overall proof could be less than 2 pages. Yeah? Depending how many diagrams you draw.
Yes, and how big you are.